There will be a moment, impossibly far in the future, when the last light in the universe flickers into existence, not from a living star, not from a galaxy, not even from the hot plasma of a quasar billions of light years away. The last light will come from something we've never seen before and never will see. A stellar corpse, so ancient, so cold, and so forgotten that it makes our sun look like a newborn infant. The last light in the universe will come from a black dwarf supernova. The universe today is 13.8 billion years old. That sounds like an eternity. It's nothing. The timeline we're about to explore makes the current age of the cosmos look like the first microsecond of creation. We're going to travel forward through timescales so vast that they break human intuition. We'll watch as every star dies, as galaxies dissolve into darkness, as even the atoms themselves may cease to exist. And at the end of this incomprehensible journey, we'll discover that the universe has one final trick left to play. Black dwarfs don't exist yet. They can't. The universe is too young. But one day, in a future so distant that the number requires 40 digits to write, every star like our sun will become one. They'll be the cold, dark, forgotten remnants of a cosmos that once blazed with light. And then, after waiting longer than the current age of the universe repeated a trillion times, some of these dead stars will explode. These won't be normal supernovas. They'll be iron supernovas, the result of quantum mechanics continuing to function in a universe that has run out of energy. They'll be the last fireworks in cosmic history, the final proof that something can still happen when it seems like nothing remains possible. Today, we're going to understand how stars die, how they stay dead, and how some of them will achieve one last moment of violent glory in a cosmos that has long since grown dark and silent. You exist in what future cosmologists might call the stelliferous era, the age of stars. It's a brief and brilliant moment in cosmic history when hydrogen fusion powers billions of suns, creating light, heat, and the heavy elements necessary for planets and life. This era will not last forever. In fact, on cosmic timescales, it's already almost over. To understand why, we need to start with the life cycle of ordinary stars like our sun and follow them to their ultimate fate as crystallized diamonds floating in the eternal darkness. Our sun has been burning for 4.6 billion years. That's already a third of its total lifetime. It fuses hydrogen into helium in its core, releasing energy that creates the light and warmth that makes life on Earth possible. This process is incredibly efficient. Every second, the sun converts about 600 million tons of hydrogen into helium, losing 4 million tons of mass in the process. That missing mass becomes energy according to Einstein's famous equation. The sun will continue this process for another 5 billion years or so before it runs into a problem. The problem is simple but unavoidable. The sun is gradually running out of hydrogen fuel in its core. As hydrogen depletes, the core contracts and heats up, causing the outer layers to expand dramatically. The sun will swell into a red giant, growing so large that it will likely engulf Mercury and Venus, possibly even Earth. During this phase, the sun's outer layers will be only loosely bound to the core. Solar winds will gradually blow these layers away, creating a beautiful planetary nebula, a shell of glowing gas expanding into space. What remains after this dramatic transformation is the core itself. No longer able to sustain the nuclear fusion that powered it for billions of years, the core becomes what astronomers call a white dwarf. This object is roughly the size of Earth, but contains about 60% of the sun's original mass. To understand how dense this is, imagine compressing a school bus into the size of a sugar cube. A teaspoon of white dwarf material would weigh about 15 tons on Earth. This extreme density creates conditions unlike anything we experience in everyday life. White dwarfs don't generate energy through fusion. They're not burning anything. Instead, they shine simply by radiating away the heat they inherited from their parent star's core. Think of a white dwarf as a cooling ember, glowing not because it's actively burning, but because it's still hot from when it was created. The surface temperature of a newly formed white dwarf can exceed 100,000 degrees Celsius, making it appear brilliant white or even bluish white when viewed through a telescope. But here's where things get interesting. White dwarfs are supported not by fusion or by ordinary gas pressure, but by something called electron degeneracy pressure. This is a quantum mechanical effect that prevents electrons from being squeezed too close together. According to the Pauli exclusion principle, no two electrons can occupy the same quantum state simultaneously. When you compress matter to white dwarf densities, electrons are forced into higher and higher energy states because the lower ones are all occupied. This creates an outward pressure that supports the star against gravitational collapse. This quantum pressure is remarkable because it doesn't depend on temperature. A white dwarf could be at absolute zero and still remain supported against gravity. The electron degeneracy pressure would persist as long as the electrons exist. This means white dwarfs don't collapse when they cool down. They simply become cooler and cooler versions of themselves, gradually radiating their heat into space over trillions of years. The universe contains hundreds of billions of white dwarfs, probably more. Every star, with a mass between about 0.5 and 8 times the Sun's mass, will eventually become a white dwarf. More massive stars explode as supernovas and leave, behind neutron stars or black holes. Less massive stars take longer than the current age of the universe to complete their evolution, so we haven't seen them die yet. But the sweet spot, the stars that make up the vast majority of stellar deaths in cosmic history, all end as white dwarfs. Astronomers have catalogued thousands of these stellar corpses. Sirius B, the companion to the brightest star in our night sky, is a white dwarf about the mass of the Sun, compressed into a sphere smaller than Earth. Procyon B, another nearby white dwarf, orbits the 8th brightest star visible from Earth. 40 Eridani b was the first white dwarf ever discovered, spotted in 1783 by William Herschel, though its true nature wasn't understood for another century and a half. These objects are everywhere, scattered throughout the galaxy, slowly cooling in the darkness. The nearest white dwarf to Earth is only 8.6 light-years away. It's called Sirius B, and it orbits the star Sirius A every 50 years. Sirius B is about 25,000 times fainter than its companion, despite having about the same mass. This illustrates just how small and dense white dwarfs are compared to normal stars. If you could somehow stand on the surface of Sirius B, you would weigh about 4 million times what you weigh on Earth. Your body would be crushed instantly into a thin layer of compressed atoms. White dwarfs come in several varieties depending on their composition and temperature. The hottest and youngest are called Da white dwarfs, dominated by hydrogen in their thin atmospheres. As they cool, some develop helium-dominated atmospheres and are classified as Db white dwarfs. Others show traces of carbon, oxygen, or even metals in their spectra. These atmospheric signatures provide clues about the star's history and the nuclear processing that occurred in its progenitor star. But beneath those thin atmospheres, something extraordinary is happening. Something that transforms these stellar corpses into the largest diamonds in the universe. When a white dwarf first forms, its interior is a hot, dense plasma of carbon and oxygen nuclei, surrounded by a sea of degenerate electrons. The nuclei move freely, vibrating and colliding in the intense heat left over from the star's final fusion reactions. But as the white dwarf cools over billions of years, the motion of these nuclei begins to slow down. The thermal energy decreases while the electrostatic forces between nuclei remain constant. Eventually, the attractive forces between nuclei become stronger than their kinetic energy. At this point, the nuclei begin to arrange themselves into a crystalline lattice, a highly ordered structure where each nucleus occupies a specific position relative to its neighbors. The white dwarf crystallizes from the inside out, starting at the center where it's coolest and gradually extending outward toward the surface. This process transforms the white dwarf from a liquid ball of plasma into a solid sphere of crystallized carbon and oxygen. This isn't a metaphor. White dwarfs literally become giant cosmic diamonds. The crystal structure is the same as diamond, a face-centered cubic lattice where each carbon atom is bonded to 4 neighbors in a tetrahedral arrangement. The only difference is scale. A diamond on Earth might contain 10 to the power of 22 carbon atoms. A crystallized white dwarf contains about 10 to the power of 56 carbon atoms arranged in a single, enormous crystal structure the size of Earth. Astronomers discovered evidence for white dwarf crystallization in 2019 using data from the Gaia Space Telescope. By measuring the precise brightnesses and colors of thousands of white dwarfs, researchers found a population of stars that were brighter than expected for their color. This extra brightness comes from the latent heat released during crystallization, similar to how water releases heat when it freezes into ice. The crystallization process releases enough energy to keep the white dwarf glowing slightly longer than it would otherwise. The transition from liquid to solid doesn't happen all at once. It takes hundreds of millions of years for the crystallization front to propagate from the center to the surface. During this time, the white dwarf develops an interesting internal structure. The core is solid crystal. The outer layers are still liquid plasma, and there's a transition zone where solid and liquid coexist, with crystals forming and dissolving in a constantly shifting boundary. As the white dwarf continues to cool, the crystallization proceeds until the entire star is solid. At this point, the white dwarf consists of a crystalline core surrounded by thin layers of lighter elements, and finally, a thin atmosphere of hydrogen or helium. The whole object is about as dense as a white dwarf can be without collapsing into something else, and it will remain in this configuration for a very long time. How long exactly? That depends on how you define a very long time. White dwarfs cool extremely slowly because they have very small surface areas compared to normal stars. The Stefan-Boltzmann law tells us that the rate at which an object radiates energy depends on both its temperature and its surface area. White dwarfs have temperatures of thousands or tens of thousands of degrees, but surface areas only about 1/1,000,000th that of the Sun. This means they radiate energy very slowly. The oldest white dwarfs in the Milky Way are about 11 billion years old, nearly as old as the galaxy itself. These ancient stellar corpses have cooled from initial temperatures of 100,000 degrees Celsius to about 3,000 degrees Celsius. They appear deep red, barely visible even through powerful telescopes, but they're still glowing, still radiating the heat from their formation billions of years ago, and they will continue glowing for trillions of years more. Here's where the numbers start to get truly astronomical. The coolest white dwarfs we can detect today have surface temperatures around 2,500 degrees Celsius. They're glowing deep infrared, barely emitting any visible light at all. To cool from 100,000 degrees to 2,500 degrees takes about 10 billion years. But to cool from 2,500 degrees to 5 degrees above absolute zero, that takes approximately 10 quadrillion years. That's a 1 followed by 16 zeros, a million billion years. The universe has existed for only 13.8 billion years. White dwarfs will continue cooling for 1,000,000 times longer than the universe has existed so far. During this incomprehensible cooling period, the white dwarf passes through several stages. Initially, it cools relatively quickly, going from blue-white to yellow to red over the first few billion years. This is the stage where most white dwarfs exist today. Then the cooling slows dramatically. Going from red to infrared takes tens of billions of years. Going from bright infrared to dim infrared takes hundreds of billions of years. Eventually, after about 100 trillion years, the white dwarf becomes so cool that it no longer emits any detectable radiation. Its surface temperature approaches the cosmic microwave background radiation, the remnant heat from the Big Bang itself. At this point, the white dwarf transitions from being a white dwarf to being something we've never observed and never will observe in our lifetimes or for trillions of years after. It becomes a black dwarf. The name is somewhat misleading. Black dwarfs aren't black in the sense of being black holes. They're black in the sense of being invisible, of no longer emitting enough light to be detected by any telescope. They're the ultimate stellar corpses, the cold, dark remnants of stars that died so long ago that even their heat has been radiated away into the void. Black dwarfs are theoretical objects. None exist yet because the universe isn't old enough for any white dwarf to have cooled completely. Even the oldest white dwarfs in the universe, those that formed from the first generation of stars more than 13 billion years ago, are still hot enough to glow faintly in the infrared. They'll remain visible for trillions of years more. The first black dwarf won't form for at least 10 quadrillion years, perhaps much longer depending on the exact cooling rate and the definition of black we use. Think about that timeline. The universe is currently 13.8 billion years old. The Sun will become a white dwarf in about 7 billion years. That white dwarf will cool for another 10 quadrillion years before becoming a black dwarf. That's 700,000 times longer than the current age of the universe. If the age of the universe so far were compressed into a single second, the time for the Sun's remnant to become a black dwarf would be 8 days. But we can go even further with these comparisons. If the current age of the universe were represented by a single meter, the time for a white dwarf to become a black dwarf would be a distance of 700 kilometers. If the universe's age so far were 1 hour, the cooling time would be 80 years. No matter how you scale it, the conclusion remains the same. Black dwarfs exist in a future so remote that it might as well be infinity compared to any human timescale. During this cooling period, several things happen to the universe around these dying stars. First, all the normal stars will have died. Red dwarfs, the smallest and longest-lived stars, can burn for trillions of years, but even they will eventually exhaust their fuel. By the time black dwarfs start to form, the last red dwarf will have faded billions of years earlier. The stelliferous era, the age of stars, will be over. Second, galaxies will have changed dramatically or ceased to exist as distinct structures. Stars gradually lose energy through gravitational interactions and by emitting gravitational waves. Over trillions of years, some stars will fall into the central black holes of their galaxies. Others will be ejected into intergalactic space. Galaxy clusters will disperse. The organized structure we see today, with galaxies grouped into clusters and superclusters, will dissolve into isolation. Third, planets will no longer exist in any recognizable form. Earth will have been destroyed when the Sun became a red giant. Any planets that survived will gradually spiral into their parent white dwarfs or be ejected from their systems through gravitational interactions. The solar system as we know it will be gone, replaced by a single cooling stellar corpse drifting alone through space. Fourth, the cosmic microwave background radiation will have cooled dramatically. Today, this radiation has a temperature of 2.7 degrees Kelvin, just barely above absolute zero. But as the universe expands, this radiation cools. In 10 quadrillion years, the cosmic microwave background will have a temperature of less than 1/1,000,000th of a degree above absolute zero. The universe itself will be cold, dark, and effectively empty from any human perspective. This is the environment where black dwarfs exist, a cosmos that has run out of fuel, run out of light, and run out of energy. A universe in the deep freeze, where the temperature everywhere is essentially absolute zero, where no stars shine because no stars remain, where galaxies have dissolved and planets have fallen into oblivion. A universe that seems dead, frozen, unchanging. But it's not unchanging. Even in this frozen wasteland, physics continues to operate. Quantum mechanics doesn't care whether the universe is young and vibrant or old and dead. The laws of nature persist, and those laws have one more trick to play. Let's examine the timescales more carefully, because understanding them is crucial to grasping just how far in the future we're talking about. Cosmologists divide the far future into several distinct eras, each characterized by different dominant processes. We currently live in the stelliferous era, which began about 100 million years after the Big Bang, when the first stars formed, and will last until the last stars die. The stelliferous era will end in approximately 100 trillion years. That's 10 to the power of 14 years, 100,000 billion years. By this time, even the smallest red dwarf stars will have exhausted their hydrogen fuel and become white dwarfs. The last natural light in the universe will have gone out. No more fusion will occur except in very rare circumstances we'll discuss later. After the stelliferous era comes the degenerate era, named after the degenerate matter that white dwarfs are made of. This era lasts from about 10 to the power of 14 years until about 10 to the power of 40 years. During this time, the universe is dominated by stellar remnants, white dwarfs, neutron stars, and black holes. These objects don't generate new energy, but they still have heat left over from their formation. They slowly radiate this heat away into space. The early part of the degenerate era is when white dwarfs cool into black dwarfs. The timeline varies depending on the white dwarf's mass and composition, but most estimates suggest that typical white dwarfs become black dwarfs somewhere between 10 to the power of 15 and 10 to the power of 30 years into the future. That's a range of uncertainty spanning 15 orders of magnitude, which tells you how difficult these calculations are and how far beyond current astronomical observations we're projecting. But even 10 to the power of 30 years is nothing compared to what comes next. Around 10 to the power of 36 years, if proton decay occurs, matter itself begins to disintegrate. Protons, the building blocks of atomic nuclei, may not be stable over these vast timescales. Theoretical models in particle physics suggest that protons could decay into lighter particles like positrons and photons. If this happens, black dwarfs would gradually evaporate as their constituent protons disappear. The evidence for proton decay remains ambiguous. Experiments have placed lower limits on the proton lifetime of at least 10 to the power of 34 years, meaning that if protons decay at all, they take longer than this to do so. But some grand unified theories predict proton decay on timescales of 10 to the power of 36 to 10 to the power of 45 years. If these theories are correct, black dwarfs and all other matter made of protons will gradually disappear during the late degenerate era. Assuming protons are stable or decay on timescales longer than 10 to the power of 40 years, the universe eventually enters what cosmologists call the black hole era. During this period, the only significant sources of energy in the universe are black holes slowly evaporating through Hawking radiation. This process, predicted by Stephen Hawking in 1974, occurs because quantum fluctuations near a black hole's event horizon can create particle-antiparticle pairs. Occasionally, one particle falls into the black hole while the other escapes, causing the black hole to gradually lose mass. The rate of Hawking radiation is inversely proportional to the black hole's mass. Small black holes evaporate quickly, large ones evaporate slowly. A black hole with the mass of the Sun would take 10 to the power of 67 years to evaporate completely. Supermassive black holes, with millions or billions of solar masses, would take 10 to the power of 100 years or longer. These timescales are so vast that they make the formation time of black dwarfs look instantaneous by comparison. After all, the black holes have evaporated, the universe enters its final stage, the dark era. This is a cosmos containing only cold black dwarfs, assuming protons don't decay, along with wandering electrons, positrons, neutrinos, and photons. The temperature everywhere is essentially absolute zero. The density of matter is incredibly low because expansion has spread everything across vast distances. No energy sources remain capable of doing work or generating heat. This is the heat death of the universe, the state of maximum entropy where no further change seems possible. The universe hasn't been destroyed. It's simply run down, like a clock that's wound down and stopped ticking. Matter still exists, but it's spread so thin and cold that nothing interesting can happen anymore. Or so it seems. These timescales are difficult to comprehend because they exceed human experience by factors so large that numbers lose meaning. Let me try some comparisons. The time for white dwarfs to become black dwarfs, 10 to the power of 15 to 10 to the power of 30 years, is longer than the current age of the universe by factors of 100,000 to 1 trillion trillion. If you represented the current age of the universe as 1 second, the time for black dwarfs to form would be somewhere between 3 years and 30 billion years, depending on which estimate you use. The time for protons to decay, if they do at all, is even longer. 10 to the power of 36 years is approximately 10 trillion times the current age of the universe. If the universe's current age were 1 second, proton decay would occur in 300 trillion years. That's 20,000 times longer than the universe has existed so far, compressed into a comparison where the universe's age is 1 second. The time for supermassive black holes to evaporate, 10 to the power of 100 years, defies all comparison. This is a Google years, a 1 followed by 100 zeros. It's longer than the current age of the universe by a factor of about 10 to the power of 90. There's no meaningful way to make this comprehensible through analogy. It's simply unimaginably vast. But here's what matters for our story. Black dwarfs form relatively early in this timeline, at least early compared to black hole evaporation. By the time the universe reaches 10 to the power of 30 years old, or certainly by 10 to the power of 40 years, most white dwarfs will have cooled into black dwarfs. These objects will be the dominant form of matter in the universe, assuming protons haven't decayed. Countless trillions of them, drifting alone through the darkness, spread across distances so vast that they'll likely never encounter each other again. These black dwarfs will be cold. Their surface temperatures will be less than 1 degree above absolute zero. They won't glow at any wavelength. They'll be invisible to any conceivable telescope. They'll be the forgotten remnants of stars that died so long ago that even the heat from their deaths has dissipated. And yet, they won't be completely inactive. Deep in their cores, something remarkable will still be happening, something that will eventually lead to the last explosions in cosmic history. The key to understanding black dwarf supernovas lies in quantum tunneling, one of the strangest phenomena in all of physics. Quantum tunneling allows particles to pass through energy barriers that classical physics says should be impossible to cross. It's the reason. Radioactive nuclei decay, the mechanism behind the scanning tunneling microscope, and the process that allows nuclear fusion to occur in the Sun at temperatures lower than classical physics would predict. Here's how tunneling works. In classical physics, a particle needs enough energy to overcome a potential barrier. Imagine rolling a ball toward a hill. If the ball doesn't have enough kinetic energy to reach the top of the hill, it will roll back down. It cannot get to the other side unless you give it more energy. This makes intuitive sense based on everyday experience. Quantum mechanics changes this picture completely. In quantum theory, particles don't have definite positions and velocities. Instead, they exist in states described by wave functions that give the probability of finding the particle at any location. These wave functions can extend through energy barriers that would block a classical particle. This means there's a small but non-zero probability that a particle can appear on the other side of a barrier, even if it doesn't have enough energy to go over the top. The probability of tunneling decreases exponentially with the barrier's height and width. High barriers or wide barriers are very difficult to tunnel through, but given enough time, even incredibly unlikely tunneling events will eventually occur. And in the far future, time is the one resource the universe has in infinite supply. Inside a black dwarf, nuclei sit in a crystalline lattice, barely moving because the temperature is so low. These nuclei are separated by the electromagnetic repulsion between their positive charges. For two nuclei to fuse and release energy, they need to get close enough for the strong nuclear force to bind them together. But the electromagnetic barrier preventing this is enormous at low temperatures. In normal stars, fusion occurs because the nuclei have high kinetic energy from the extreme heat. They collide with enough force to overcome most of the electromagnetic barrier, and quantum tunneling helps them through the last bit. In the Sun's core, which is 15 million degrees Celsius, hydrogen nuclei tunnel through the final portion of their electromagnetic barrier and fuse into helium. This is why the Sun shines. But black dwarfs are cold. Their interior temperatures are measured in degrees above absolute zero, not millions of degrees. The nuclei have essentially no kinetic energy. They sit in their crystal lattice positions, vibrating slightly but not colliding with any significant force. Classical physics says that no fusion should occur under these conditions. The nuclei don't have enough energy to approach each other closely enough for the strong force to bind them. Quantum mechanics says otherwise. Given enough time, nuclei in a black dwarf will occasionally tunnel through the entire electromagnetic barrier and fuse together. The probability for any individual fusion event is incredibly small. The timescale for such events is measured not in years or billions of years, but in time periods that make the current age of the universe look like an eye blink. But the universe has time, infinite time, or close enough, and when you have infinite time, even the most improbable events become inevitable. A paper published by physicists Fred Adams and Gregory Laughlin explored this process in detail. They calculated the timescales for various quantum tunneling fusion reactions in stellar remnants and found something remarkable. Even in the frozen darkness of the far future, fusion continues at a glacially slow pace, converting lighter elements into heavier ones. The fusion doesn't release enough energy to warm the black dwarf or make it glow. The heat is radiated away into space immediately, maintaining the black dwarf at essentially the same temperature as its surroundings. But over time, scales of 10 to the power of 1,500 years, yes, that's 10 to the power of 1,500, not 10 to the power of 15, fusion will convert significant fractions of the black dwarf's carbon and oxygen into heavier elements. Most of this fusion produces elements like neon, magnesium, and silicon. These elements are more stable than carbon and oxygen in the sense that fusing them together releases additional energy. The fusion proceeds gradually, building heavier and heavier elements through a series of quantum tunneling events. Carbon fuses to form heavier elements. Oxygen fuses. The resulting products fuse with each other, or with remaining carbon and oxygen. This process continues for unimaginable timescales. Each step in the fusion chain requires quantum tunneling through enormous energy barriers. Each step is individually unlikely beyond comprehension, but with enough time, the chain continues. Neon fuses to form heavier elements. Magnesium fuses, silicon fuses. The black dwarf slowly, incrementally converts its composition from carbon-oxygen to a mixture of heavier elements. Eventually, after timescales that make 10 to the power of 1,500 years look short by comparison, this process reaches its inevitable conclusion. The fusion produces iron. Iron is special in nuclear physics. It's the most stable element. Fusing lighter elements into iron releases energy. Fusing iron into heavier elements requires energy input. Stars can't produce elements heavier than iron through normal fusion because there's no energy benefit to doing so. In a black dwarf, the slow accumulation of iron through quantum tunneling fusion represents the end of the line. Once nuclei become iron, they won't fuse further because doing so would require energy input, and the black dwarf has no energy source to provide this. The iron accumulates in the black dwarf's core, gradually building up over timescales that dwarf everything else we've discussed. Here's where things get explosive. There's a limit to how much mass a white dwarf or black dwarf can have, called the Chandrasekhar limit, after the astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930. This limit is approximately 1.4 times the mass of the Sun. White dwarfs more massive than this cannot be supported by electron degeneracy pressure alone. They must either have additional support from other sources, or they must collapse. When a white dwarf approaches the Chandrasekhar limit through accretion of matter from a companion star, it becomes unstable. The electron degeneracy pressure that has been supporting it against gravity is no longer sufficient. The white dwarf begins to collapse. As it collapses, it heats up dramatically. This heating triggers runaway fusion reactions that tear the star apart in a thermonuclear explosion called a Type Ia supernova. Type Ia supernovas are some of the brightest events in the universe, temporarily outshining entire galaxies. They're caused by white dwarfs that exceed the Chandrasekhar limit and explode. Astronomers use them as standard candles to measure cosmic distances because they all have roughly similar brightness. These explosions are violent, luminous, and spectacular. Now imagine a similar process, but without the heat. A black dwarf composed primarily of iron, built up over unimaginable timescales through quantum tunneling fusion, gradually approaches the Chandrasekhar limit. At some point, the iron core reaches critical mass. The electron degeneracy pressure can no longer support it. The black dwarf begins to collapse. But unlike a normal type Ia supernova, this collapse doesn't initially heat the black dwarf significantly. The collapse is slow and cold. As the density increases, electrons are forced into higher energy states to maintain degeneracy pressure. Eventually, these electrons have enough energy to combine with protons in the iron nuclei, forming neutrons and releasing neutrinos. This process, called electron capture or neutronization, removes the electron degeneracy pressure that was supporting the star. Without electron pressure, the black dwarf collapses catastrophically. In a fraction of a second, an object the size of Earth collapses to a point only a few kilometers across. The collapse releases an enormous amount of gravitational potential energy. This energy drives nuclear reactions that attempt to break the iron nuclei apart and reassemble them into other elements. The result is an explosion. This is a black dwarf supernova, also called an iron supernova because the fuel is iron rather than carbon or oxygen like in normal supernovas. The explosion is similar to a type Ia supernova in mechanism, a stellar remnant exceeding the Chandrasekhar limit and exploding. But it's different in detail because the composition is different and the temperature is different. Black dwarf supernovas are expected to be less luminous than normal supernovas, perhaps only 100th to 1,000th as bright. They'll release less energy because iron is already a highly stable element, and breaking it apart or fusing it doesn't release as much energy as burning carbon or oxygen does. The explosion will be visible across vast distances, but it won't outshine galaxies like a normal supernova does. Still, in a universe that has been dark for 10 to the power of 40 years or more, even a faint explosion will be extraordinary. It will be the only significant light source in an otherwise completely dark cosmos. It will briefly illuminate a small region of space, creating photons and neutrinos that will travel outward through the void. For a brief moment, measured in hours or days, a single point in the universe will shine again. Then it will fade. The explosion will disperse the black dwarf's mass into space. The debris will cool and spread out, adding to the thin mist of particles floating through the cosmos, and the universe will return to darkness. But the explosion will have proven something important. Even in a dead universe, even after every star has gone out and every galaxy has dissolved, change is still possible. Events can still occur. The universe is not completely static. The timescale for black dwarf supernovas depends on several factors. How long does it take for quantum tunneling to convert a black dwarf's composition to iron? How massive does the black dwarf need to be to eventually exceed the Chandrasekhar limit? The calculations are uncertain because we're extrapolating physics into regimes we can never observe or test experimentally. Fred Adams and Gregory Laughlin estimated that black dwarf supernovas could begin occurring around 10 to the power of 1,100 years into the future. Other researchers have suggested timescales as long as 10 to the power of 32,000 years or even longer. The uncertainty spans multiple orders of magnitude because the quantum tunneling probabilities are so sensitive to the exact nuclear physics and the temperature of the environment. But let's use 10 to the power of 1,100 years as a representative number. This is so far in the future that the number almost loses meaning. It's a 1 followed by 1,100 zeros. Written out, it would fill several pages. It's longer than the current age of the universe by a factor of 10 to the power of 1,090. If the universe's current age were a single Planck time, the smallest meaningful unit of time in physics, the time until black dwarf supernovas would still be absurdly long. Comparisons fail at this scale. There's no way to make 10 to the power of 1,100 years comprehensible through analogy. It simply is what it is, a timescale so vast that it represents the ultimate limit of how far physics can meaningfully project into the future. Beyond this, we're speculating about speculations, extrapolating laws of nature into regimes where those laws themselves might change or become undefined. What matters is not the precise number, but the concept. Black dwarfs, the cold dead remnants of stars that died more than 10 to the power of 30 years ago, can still undergo catastrophic explosions through the cols. Slow accumulation of iron via quantum tunneling fusion. These explosions will be the last significant energy release events in cosmic history. They'll be the final supernovas, the last fireworks, the ultimate proof that the universe, no matter how dead it becomes, never reaches a state of complete changelessness. The universe will continue expanding during all of this. By the time black dwarf supernovas occur, expansion will have carried every gravitationally unbound structure to distances so vast that they can never interact again. Black dwarfs will be separated by distances measured in light years, then millions of light years, then billions of light years, eventually trillions of light years or more. Each black dwarf exists in its own isolated bubble of space, cut off from all others by the inexorable expansion of the cosmos. When a black dwarf supernova occurs, its light will travel outward at the speed of light. But due to the expansion of space, this light may never reach another black dwarf or any other object. The photons will simply spread out into an expanding void, redshifting to longer and longer wavelengths as they travel through stretching space. Eventually, the photons' wavelengths will be longer than the observable universe itself. The light from the last explosions will effectively disappear into the fabric of space-time. This raises a philosophical question. If an event occurs but no one and nothing can observe it, did it really happen? The black dwarf supernovas of the far future will be the ultimate unobserved events. They'll create light and neutrinos and gravitational waves, but these signals will travel through an empty universe with no receivers. There will be no civilizations to build telescopes, no scientists to record the data, no minds to contemplate the significance. And yet, the explosions will happen. The laws of physics don't care whether anyone is watching. Quantum tunneling will continue. Iron will accumulate. Black dwarfs will exceed the Chandrasekhar limit. Explosions will occur. The universe will produce these events as inevitably as a wound-up spring releases when you let it go, even if there's no one around to hear the snap. But we've been assuming that all black dwarfs can potentially explode. This isn't quite true. The key factor is mass. Only black dwarfs with masses close to the Chandrasekhar limit have any chance of becoming supernovas. Less massive black dwarfs will never accumulate enough iron to reach critical mass, no matter how long they wait. Our Sun will leave behind a white dwarf with a mass of about 0.6 solar masses, roughly 60% of the Sun's current mass. This is well below the Chandrasekhar limit of 1.4 solar masses. Even if this white dwarf cools into a black dwarf and then accumulates iron through quantum tunneling fusion, it will never reach the mass needed to collapse and explode. The Sun's remnant will exist as a cold, dark, crystallized ball of iron for eternity, or at least until proton decay destroys it if that occurs. Most stars end their lives as white dwarfs, with masses between 0.5 and 0.9 solar masses. The majority of stellar remnants are too low in mass to ever become supernovas, even in the far future. They'll simply exist as black dwarfs forever, slowly converting their composition to iron through quantum tunneling, but never reaching the critical mass needed for collapse. But some white dwarfs are more massive. Stars with initial masses between about 6 and 8 solar masses produce white dwarfs with masses close to 1.2 or 1.3 solar masses. These objects are near the Chandrasekhar limit. They don't have quite enough mass to collapse immediately, but they're close. If these white dwarfs cool into black dwarfs and accumulate additional iron through fusion, they could potentially reach the critical mass. The exact fraction of black dwarfs that will eventually explode depends on the initial mass distribution of stars and the efficiency of the quantum tunneling fusion process. Current estimates suggest that somewhere between 1% and 10% of all black dwarfs could potentially become supernovas. This sounds like a small percentage, but given the vast number of stars in the universe, it translates to an enormous absolute number of explosions. Our galaxy, the Milky Way, contains perhaps 200 billion stars. Over the next 100 trillion years, most of these will become white dwarfs and eventually black dwarfs. If 1% of them eventually explode as black dwarf supernovas, that's 2 billion explosions in our galaxy alone. The observable universe contains over 1 trillion galaxies. The total number of black dwarf supernovas across the observable universe could be 10 to the power of 21 or more. Of course, by the time these explosions occur, the concept of our galaxy will be meaningless. The Milky Way will have merged with Andromeda and likely several other nearby galaxies. The resulting merge system will have gradually dispersed as stars are, ejected through gravitational interactions, or fall into the central black hole. There won't be recognizable galaxies anymore, just isolated stellar remnants scattered across expanding space. Still, the explosions will happen. They'll occur randomly throughout the universe, flickering briefly before fading back into darkness. Each explosion will be separated from every other by vast distances and vast expanses of time. The universe will experience isolated moments of light in an ocean of darkness and duration. Let's consider some specific examples of nearby stars and what will happen to their remnants. Sirius A, the brightest star in our night sky, has a mass of about 2 solar masses. When it dies, it will leave behind a white dwarf with a mass of roughly 1 solar mass, still below the Chandrasekhar limit. Sirius A's remnant probably won't explode. It will become a black dwarf and remain a black dwarf for eternity. Sirius B, however, already is a white dwarf. It has a mass of about 1 solar mass. Like the Sun's remnant, it's too light to ever exceed the Chandrasekhar limit through quantum tunneling fusion alone. Sirius B will cool into a black dwarf and stay that way. Procyon A, another bright nearby star, has a mass of about 1.5 solar masses. Its future white dwarf will have a mass around 0.6 to 0.7 solar masses, not enough for an eventual explosion. Procyon B, already a white dwarf with about 0.6 solar masses, faces the same fate as Sirius B and the Sun's remnant. To find candidate black dwarf supernovas, we need to look at more massive stars. Vega, with a mass of about 2.1 solar masses, will leave a white dwarf of perhaps 0.9 to 1 solar mass. Probably still not quite enough. Spica, a binary system containing 2 massive stars with masses of 11 and 7 solar masses, will produce white dwarfs, assuming the stars don't explode as supernovas instead. These remnants could be massive enough to eventually exceed the Chandrasekhar limit in the far future. But here's the interesting thing. We don't know which specific stellar remnants will become black dwarf supernovas because we can't predict the exact mass of the white dwarf that a given star will produce. The mass depends on how much material the star loses during its red giant phase, which depends on stellar winds, the star's rotation, its metallicity, and other factors. Even stars with similar initial masses can produce white dwarfs with different final masses. What we can say is that the more massive white dwarfs, those above about 1.2 solar masses, are the most likely candidates. These objects are already close to the Chandrasekhar limit. They only need a small amount of additional mass to push them over the edge. If quantum tunneling fusion can add that mass in the form of iron, they'll explode. The process works like this. A 1.2 solar mass white dwarf cools over 10 to the power of 15 to 10 to the power of 30 years, becoming a black dwarf, over the next 10 to the power of hundreds or thousands of years. Quantum tunneling slowly fuses its carbon and oxygen into heavier elements, eventually producing iron. As the iron accumulates, the black dwarf's mass doesn't change, but its composition does. Iron is denser than carbon or oxygen for a given pressure, so the black dwarf gradually becomes more compact. Eventually, the black dwarf is composed primarily of iron and has a total mass of, say, 1.38 solar masses. It's approaching the Chandrasekhar limit of 1.4 solar masses. At this point, the quantum tunneling fusion continues, But now there's a problem. Fusing iron doesn't release energy. It requires energy. The fusion effectively stops because there's no energy source to drive it. But neutronization can still occur. At high enough densities, it becomes energetically favorable for electrons to combine with protons in the iron nuclei, forming neutrons. This process removes electrons from the degenerate electron gas that's been supporting the black dwarf against gravity. As electrons disappear, the degeneracy pressure decreases. The black dwarf becomes less able to support its own weight. At some critical point, the loss of electrons triggers a runaway collapse. The black dwarf implodes, the density spikes, nuclear reactions occur, the black dwarf explodes in an iron supernova. The exact details of this explosion are uncertain because we can't model them with current computers or experiments, but the basic physics is clear enough. The black dwarf exceeds its stability limit and explodes. After the explosion, the debris disperses into space. Some of it might form a neutron star if the collapse is rapid enough and the core reaches neutron degeneracy density before the explosion blows everything apart. More likely, the explosion completely disrupts the black dwarf, leaving nothing behind except an expanding cloud of iron, neutrons, and other particles. This cloud will cool and spread out over time. The particles will eventually be so dispersed that they effectively cease to interact with each other. The iron nuclei will decay if proton decay occurs. If protons are stable, the iron nuclei will persist indefinitely, wandering through space as isolated atoms separated by vast distances, and then nothing. The region of space where the black dwarf supernova occurred returns to the same cold, dark emptiness that existed before. The explosion was a brief interruption, a momentary flicker of light and energy in an otherwise unchanging void. But it happened. It left its mark on the universe, even if no one was there to see it. We should discuss what happens after the last black dwarf supernova. This is the endgame of endgames, the point where even the final possible explosions have all occurred and nothing remains that can release significant energy. The universe has reached a state that cosmologists call the true heat death, the final equilibrium where no further change is possible. In this state, assuming protons are stable, the universe contains cold black dwarfs that have already undergone their supernova explosions, or were too low mass to explode. Neutron stars, black holes, and a thin mist of particles spreading through space. The temperature everywhere is essentially absolute zero. The density of matter is so low that you could travel for trillions of light years without encountering a single atom. The black holes are the last significant objects. They don't explode like black dwarfs. Instead, they slowly evaporate through Hawking radiation. The process takes an incredibly long time. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate completely. A black hole with 1 million solar masses would take 10 to the power of 85 years. A billion solar mass black hole would take 10 to the power of 98 years. These timescales are vastly longer than the time for black dwarf supernovas. The black dwarfs will all have exploded or remained stable long before the black holes finish evaporating. The late universe will be dominated by black holes slowly losing mass through quantum effects at the event horizon. Hawking radiation is thermal radiation. The temperature of a black hole is inversely proportional to its mass. Larger black holes are colder than smaller ones. A solar mass black hole has a temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero. A supermassive black hole is even colder, perhaps less than a trillionth of a degree above absolute zero. These black holes are colder than the cosmic microwave background radiation today. But as the universe expands and cools, the cosmic microwave background temperature drops. Eventually, perhaps around 10 to the power of 20 years or so, the cosmic microwave background becomes colder than all black holes. At that point, black holes begin to lose mass faster than they gain mass from absorbing radiation, and the evaporation accelerates. As a black hole evaporates, it gets smaller and hotter. The temperature increases inversely with mass, so as the black hole shrinks, it radiates faster. This creates a runaway process. The black hole loses mass, gets hotter, radiates faster, loses mass faster, and so on. The final moments of evaporation are explosive. The black hole releases its last bit of mass energy in a burst of high-energy photons and particles. But this explosion is tiny compared to a supernova, or even compared to a black dwarf supernova. The total energy released is equal to the black hole's mass times the speed of light squared, Einstein's equation. For a solar mass black hole, that's about 10 to the power of 47 joules, equivalent to about 10 million billion times the energy the Sun releases in its entire lifetime. That sounds like a lot, but it's released over 10 to the power of 67 years. The average power output is only about 10 to the power of negative 14 watts, far less than the heat from a human body. In the late universe, black hole evaporation provides the last source of energy. After all the black dwarfs have stopped fusing and the last black dwarf supernovas have exploded, black holes will be the only objects doing anything thermodynamically interesting. They'll slowly convert their mass into Hawking radiation, enriching the thin particle sea with occasional photons and particle-antiparticle pairs. After all, the black holes evaporate. The universe contains only low-energy particles. Photons, neutrinos, electrons, and positrons if protons have decayed, or those particles plus stable protons and neutrons if protons don't decay. These particles spread ever farther apart due to cosmic expansion. The density approaches zero. The temperature remains at absolute zero, or as close to it as quantum mechanics allows. This is the true heat death, the final state of maximum entropy. No gradients exist. No energy flows. No processes capable of doing work remain active. The universe is uniformly cold, dark, and empty everywhere. Nothing changes because there's no energy available to drive change. Or is there? Some physicists have speculated that even in heat death, quantum fluctuations could still occur. These fluctuations might spontaneously create particles or even macroscopic objects from the vacuum. Given infinite time, quantum fluctuations could in principle create anything, including a fully formed human brain, complete with memories and consciousness. These hypothetical entities are called Boltzmann brains, after the physicist Ludwig Boltzmann, who explored related ideas in the late 1800s. A Boltzmann brain is a consciousness that spontaneously forms due to random fluctuations rather than evolving through biological or technological processes. The probability of forming a Boltzmann brain is incredibly small, but in an infinite universe with infinite time, small probabilities become certainties. The formation rate of Boltzmann brains depends on the exact state of the vacuum and the properties of quantum field theory. Some calculations suggest that Boltzmann brains might form on timescales of 10 to the power of 10 to the power of 50 years or longer. These numbers are so large they don't fit in normal notation. They require stacked exponents. It's 10 to the power of a number that itself requires 50 digits to write. At these scales, even calling them time scales feels wrong. We've left the realm of physics and entered pure mathematical speculation. Whether Boltzmann brains actually form, whether consciousness can exist in such contexts, whether the vacuum really fluctuates in ways that allow their formation, these are open questions that current physics cannot definitively answer. Some cosmologists argue that in a true heat-death state, no observers can exist to define concepts like time or change. If nothing happens, and no one is there to measure it not happening, does time still pass? This edges into philosophy rather than physics. The mathematical equations still describe a universe with a time coordinate that continues to increase. But whether that coordinate has physical meaning in the absence of any physical change is debatable. Other cosmologists suggest that quantum mechanics might allow the vacuum itself to tunnel from one state to another, potentially creating new regions of space with different physical properties. These vacuum fluctuations could spawn baby universes that bud off from the parent universe and evolve independently. If this process occurs, the heat death isn't truly final. It's just the local state of our particular region of space. Other regions, created through vacuum tunneling, might be young and vibrant. This is speculative cosmology, ideas based on extending known physics into regimes where we have no experimental data and no way to test predictions. But it's what physicists do when thinking about the ultimate far future. They take the laws we understand, extrapolate them as far as possible, and see what the mathematics says. Sometimes the mathematics says nothing interesting happens. Sometimes it says incredibly weird things might happen. Black dwarf supernovas fall into the second category. The philosophical implications of black dwarf supernovas are profound. They demonstrate that the universe, no matter how old or how dead it becomes, never truly reaches a state of complete stasis. Even 10 to the power of 1,100 years in the future, events can still occur. Change is still possible. The universe has not ended, it's simply changed into a form we find difficult to imagine. This has implications for theories about the nature of time and change. Some philosophers have argued that time is defined by change. If nothing changes, time doesn't pass. But black dwarf supernovas show that change continues even in states that appear completely static. The universe never reaches a state where absolutely nothing happens. Something, somewhere, is always changing, even if only through quantum tunneling on timescales, too vast for human comprehension. It also raises questions about determinism and the arrow of time. The laws of physics are time reversible at the microscopic level. If you filmed a collision between two particles and played it backwards, it would look just as valid as the forward version. But thermodynamics and the arrow of time emerge from statistical effects in systems with many particles. Entropy increases, systems evolve from ordered to disordered states, and time has a direction. Black dwarf supernovas are consistent with this arrow of time. They represent the final dissipation of energy from the early universe. The Big Bang created a universe in a low entropy state, full of energy and structure. That energy and structure have been gradually dissipating for 13.8 billion years. Stars form and die. Black holes form and evaporate, and entropy increases. Black dwarf supernovas are the last gasp of this process, the final release of energy before the universe reaches maximum entropy. But there's something poetic about black dwarf supernovas. They're not just the end of a process, they're evidence that the universe has a kind of memory. The iron that accumulates in a black dwarf is iron that was created through quantum tunneling fusion over timescales of 10 to the power of hundreds or thousands of years. That iron represents the integrated effect of countless quantum events, each individually unlikely but collectively inevitable. When the black dwarf finally exceeds the Chandrasekhar limit and explodes, it's not a random event. It's the culmination of a process that began when the original star formed, continued through the star's main sequence lifetime, persisted through the red giant phase and the formation of the white dwarf, carried on through the cooling into a black dwarf, and finally reached its conclusion through patient quantum tunneling. The explosion is the ultimate consequence of the star's initial formation, played out over timescales that make stellar lifetimes look like microseconds. In a sense, every black dwarf supernova is a message from the distant past. The star that created that black dwarf died more than 10 to the power of 30 years ago. The civilization that might have observed that star, if any existed, is gone. The galaxy that contained the star has dissolved, but the physics that governed the star's formation and evolution continues to operate. And eventually, that physics produces one last explosion, a final validation that the laws of nature persist even when everything else has faded away. There's also a kind of cosmic justice in black dwarf supernovas. Stars that are too small to become supernovas during their lifetimes get a second chance in the far future. Our sun will never experience the glory of a supernova explosion. It's too low mass. When it dies, it will simply shed its outer layers and leave behind a cooling white dwarf. No drama, no spectacular light show, just a gradual fade into darkness. But if the sun's white dwarf were somehow able to accumulate enough additional mass, perhaps by merging with another white dwarf or through some other process, it could potentially become a supernova in the far future as a black dwarf, Not a typical black dwarf supernova driven by quantum tunneling, since the Sun's remnant is too low mass for that. But perhaps through some other mechanism we haven't considered. Of course, the probability of such events is vanishingly small. White dwarfs are spread too far apart to merge in any realistic time frame, especially after galaxies dissolve and stellar remnants are scattered across expanding space. But the fact that the physics allows for such possibilities, even if they never actually occur, is remarkable. The real candidates for black dwarf supernovas are remnants of more massive stars, white dwarfs with masses above 1.2 solar masses. These objects already had relatively dramatic lives. Their progenitor stars burned bright and hot, fusing elements up to carbon and oxygen or beyond. They lived for only millions or billions of years rather than the trillions of years that low-mass stars enjoy, and they left behind relatively massive remnants. These massive white dwarfs cool into black dwarfs like all the others, but they carry with them the potential for one final act. Through quantum tunneling, they gradually build iron cores, and eventually, in the far future, they exceed the Chandrasekhar limit and explode. They get to be supernovas after all, just delayed by 10 to the power of 1,100 years or so. Let's think about what it would be like to witness a black dwarf supernova if any conscious being could exist that far in the future. You would be floating in a dark, cold universe. No stars shine anywhere. No galaxies glow in the distance. The cosmic microwave background has cooled to essentially zero temperature. Space itself is black, not the black of an absence of light, but the black of a complete lack of any light source. Then, suddenly, a point of light appears. It's faint, far fainter than any supernova visible in today's universe. It's only 100th or 1,000th as luminous as a typical Type Ia supernova. But in the absolute darkness surrounding you, it's blazingly bright. It's the only thing you can see in any direction, the only light in the universe. The light would be reddish, shifted toward longer wavelengths by the cooling of the universe and the expansion of space. The spectrum would show the characteristic signatures of iron and other heavy elements, but spread out and dim. If you had a spectrograph, you could analyze the light and deduce what happened. An iron-rich object exceeded its stability limit and exploded. The light would persist for days or weeks, gradually fading as the explosion debris expands and cools. Then it would disappear, leaving you once again in complete darkness. That single explosion might be the only event you could observe in trillions upon trillions of years. The next nearest black dwarf supernova might be billions of light years away and billions of years in the future or past. You would have witnessed a unique event, never to be repeated in your location in space-time. Of course, no conscious being will actually witness a black dwarf supernova. The conditions necessary for consciousness, complex chemistry, metabolism, information processing, require energy gradients and structured environments. In the far future, when black dwarf supernovas occur, no energy gradients exist except for the brief moments during the explosions themselves. And those explosions are too short-lived and too isolated to support anything resembling life or consciousness. So, black dwarf supernovas will occur unobserved. They'll create light that travels outward through empty space, photons that will never interact with anything because there's nothing left to interact with. The explosions will happen not because the universe needs them to, or because they serve any purpose, but simply because the laws of physics say they must happen given enough time. This is perhaps the most profound aspect of black dwarf supernovas. They demonstrate that the universe operates according to mathematical laws that continue to function regardless of whether those laws produce anything interesting or whether anyone is around to observe the results. The laws don't care about observers or meaning or purpose. They simply describe what happens when you start with certain initial conditions and let time evolve forward. Black dwarf supernovas are inevitable consequences of quantum mechanics and general relativity applied to stellar remnants over immense timescales. They're not special events that the universe is trying to produce. They're just what happens when you combine the Pauli exclusion principle, the Heisenberg uncertainty principle, the nature of the strong and weak nuclear forces, and the warping of space-time by mass, then weight 10 to the power of 1,100 years. In a sense, the fact that black dwarf supernovas will occur tells us something deep about the nature of physical law. Laws are constraints on what's possible, not prescriptions for what must happen. The laws of physics don't say black dwarf supernovas will occur at this specific time and place. They say, given these conditions and enough time, black dwarf supernovas are possible. The universe then explores all possible outcomes over sufficient timescales, and black dwarf supernovas are among those possibilities. This raises interesting questions about the nature of probability and possibility in an infinite or effectively infinite universe. If you wait long enough, do all possible events eventually occur? Does probability become meaningless when time is unlimited? These are questions that physics can't fully answer because they involve extrapolating known laws into regimes where those laws might break down or where new physics we don't yet understand might become important. Some physicists speculate that the laws of physics themselves might change over extreme timescales. If constants of nature like the strength of fundamental forces or the mass of particles can vary, then projections about black dwarf supernovas might be wrong. The quantum tunneling rates might be different. The Chandrasekhar limit might shift. The whole process might unfold differently than our current understanding predicts. But current physics suggests the laws are stable. Constants appear to be constant. The forces don't seem to weaken or strengthen over time. This implies that black dwarf supernovas really will occur, or at least that they'll occur if protons don't decay first. If protons decay on timescales shorter than 10 to the power of 1,100 years, then black dwarfs will disintegrate before they can accumulate enough iron to explode. The jury is still out on proton decay. Grand unified theories predict it should occur, but experiments haven't detected it yet. The lower limit on proton lifetime is currently around 10 to the power of 34 years. If the actual lifetime is 10 to the power of 36 years, then protons will decay long before black dwarf supernovas occur. The black dwarfs themselves will gradually evaporate as their constituent protons and neutrons decay into lighter particles. In that scenario, black dwarf supernovas never happen. The universe skips straight from the era of black dwarfs to the era of pure radiation and leptons. The ion accumulation process is interrupted by the wholesale decay of matter. The universe reaches heat death without experiencing those final explosions. But if protons are stable, or if their lifetime exceeds 10 to the power of 1,100 years, then black dwarf supernovas represent the true final act of cosmic evolution. They're the last significant energy release events in the history of the universe. After they're done, nothing remains that can explode or shine or do anything thermodynamically interesting. The universe has truly reached its final equilibrium state. Either way, whether black dwarf supernovas occur or not, the far future looks remarkably similar. A cold, dark, empty void spreading in all directions. Particles separated by vast distances. No structure, no complexity, no change, except for the slow tick of time itself. The universe becomes an infinite, featureless expanse of nothing much at all. This vision of the far future is bleak by human standards. We evolved in an environment rich with structure and change. Our brains are adapted to detect patterns, respond to stimuli, and navigate complex environments. A universe that's uniformly cold and empty doesn't just lack conditions for life. It lacks conditions for anything we would recognize as interesting or meaningful. But the universe doesn't care about human standards of interestingness. It's not trying to be meaningful or purposeful. It's simply evolving according to physical laws from initial conditions set up at the problem, Big Bang. Those laws happen to produce a brief era of complexity and structure, the Stelliferous era, followed by an unimaginably long era of simplicity and stasis. That's just how the mathematics works out. Some philosophers and scientists have argued that this far future fate of the universe has implications for the meaning of our current existence. If everything will eventually fade into cold darkness, if all the complexity we see today is just a temporary fluctuation in the universe's march toward heat death, does that make our lives meaningless? The answer depends on your philosophical perspective. From a purely physical standpoint, meaning is a concept that emerges from conscious minds, not from the universe itself. The universe doesn't have purposes or values. It has laws and initial conditions. Everything else follows from those. But conscious beings can create meaning even in a universe that's ultimately doomed to heat death. The fact that we exist at all, that the universe passed through a phase where stars could form and planets could evolve, life and consciousness could emerge, is remarkable. We're incredibly lucky to exist during the brief stelliferous era when the universe is interesting. Black dwarf supernovas remind us that even in the far future, even when it seems like everything has ended, physics continues to operate. The universe continues to evolve. Events still occur. This suggests that the concept of ending is more subtle than it appears. The universe doesn't end in the sense of ceasing to exist. It transitions from one state to another. And those transitions, no matter how slow or how cold, are still physical processes governed by the same laws that govern everything else. There's something oddly comforting about black dwarf supernovas. They tell us that the universe has staying power. It doesn't run down and stop like a clockwork machine. It continues indefinitely, finding new ways to change and evolve even after every obvious source of change has been exhausted. Quantum mechanics ensures that nothing is truly permanent or truly static. Everything has a non-zero probability of changing state given enough time. This applies not just to black dwarfs, but to everything. Protons might decay, black holes might evaporate. The vacuum itself might tunnel to a different energy state. The universe we see today is just a snapshot of an ongoing process that extends indefinitely into the past and future. We happen to exist during a particular phase of that process, but the process continues with or without us. Black dwarf supernovas are a reminder that we're temporary, but the universe is not. They're evidence that timescales exist beyond human comprehension and that physical processes continue on those scales, whether we're here to observe them or not. They're the ultimate long-term consequence of stellar evolution, the final chapter in the story of how matter behaves under the influence of gravity and quantum mechanics. And perhaps most importantly, black dwarf supernovas demonstrate that our intuitions about endings are limited by our experience. When we think about things ending, we imagine them reaching a final state and staying there forever. But physics suggests there's no such thing as a truly final state. Every configuration of matter and energy has some probability of transitioning to another configuration. Given infinite time, all possible transitions will occur. This means the universe doesn't end so much as it continually transforms. Each era transitions into the next. The stelliferous era becomes the degenerate era. The degenerate era becomes the black hole era. The black hole era becomes the dark era. And perhaps the dark era becomes something else we can't yet imagine, driven by physics we don't yet understand. Black dwarf supernovas are the exclamation point at the end of one of these eras. They're the last fireworks show before the universe settles into its next phase. They're proof that even in the darkness, even in the cold, even when it seems like nothing could possibly happen, the universe still has tricks up its sleeve. We'll never see a black dwarf supernova. Humanity will be gone long before they occur. The sun will die, Earth will be destroyed, and any remnant of our civilization will have faded into the background radiation billions of years before the first black dwarf cools enough to begin the quantum tunneling process. We exist in an epoch separated from black dwarf supernovas by a gulf of time so vast that no human language has words to describe it. But we can imagine them. We can use mathematics and physics to predict what will happen. We can understand the processes that will lead to those final explosions. And in that understanding, we connect ourselves to the deepest rhythms of the cosmos, to processes that operate on timescales billions of trillions of times longer than human lifespans. The universe began 13.8 billion years ago, in a hot, dense state we call the Big Bang, it expanded and cooled, atoms formed, stars ignited, galaxies assembled, planets coalesced. Life emerged, at least on one planet we know of. Consciousness arose. And now, 13.8 billion years later, some of those conscious beings are capable of understanding not just how the universe began, but how it will end. We can project forward through time, watching in our mind's eye as the last stars fade, as white dwarfs cool into black dwarfs, as quantum tunneling slowly builds iron cores, and as those cores eventually exceed their stability limits and explode in the last significant light the universe will ever produce. We can't observe these events directly, but we can know they will happen. That knowledge is itself remarkable. It demonstrates the power of human reason and mathematics to transcend the limitations of human senses and lifespans. We're tiny creatures living for insignificant periods on an insignificant planet around an insignificant star. Yet we can comprehend the fate of the entire cosmos over timescales that make our existence look like a quantum fluctuation. Black dwarf supernovas are the ultimate test of that comprehension. They occur so far in the future that they push our understanding to its limits. They require extrapolating known physics across 1,100 orders of magnitude in time. They depend on quantum effects that are vanishingly unlikely but inevitable given sufficient waiting time. They represent the intersection of general relativity, quantum mechanics, thermodynamics, and cosmology in a regime where all those theories are stretched to their breaking points. And yet, we can discuss them. We can calculate when they'll occur and what they'll look like. We can understand why they're inevitable and what they mean for the long-term fate of matter in the universe. We can't observe them, but we can know them, and that knowledge is a triumph of human intellect and scientific method. So, here we stand, 13.8 billion years after the Big Bang, contemplating events that will occur 10 to the power of 1,100 years in the future. We're looking forward across a span of time so vast that the age of the universe so far is less than the briefest instant in comparison. And we're seeing with the eye of mathematics and physical law the last lights that will ever shine. Black dwarfs don't exist yet. They won't exist for quadrillions of years. And they won't explode for incomprehensibly longer than that. But they will exist. They will explode. And when they do, they'll prove one final time that the universe, no matter how old or how dead it becomes, never completely stops changing. Even in the darkness, even in the cold, even at the very end of everything, something can still happen. Those explosions will be the last fireworks in cosmic history. They'll be faint and brief, and utterly alone in an infinite dark void. No one will see them, no one will record them, no one will remember them. But they'll happen anyway, because physics says they must. And in that inevitability, in that final validation of natural law operating in the absence of any observer or meaning or purpose, there's a kind of austere beauty. The universe will go on, time will pass, and somewhere in the incomprehensible future, a black dwarf will exceed the Chandrasekhar limit, collapse, and explode. For a brief moment, a pinpoint of light will appear in the eternal darkness, and then it will fade, and the universe will return to silence. But the universe will not be quite the same as it was before. One more black dwarf will have had its moment. One more voice will have spoken in the darkness. One more star will have had its day. Even if that day came a trillion 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 years too late.